Okay, welcome back, everybody. Now let's dive into a variational autoencoder. This is a type of autoencoder that is motivated toward a different thing, a different deal than the traditional autoencoder and its deeper version. The objectives for this module is for you to know the elements of a variational autoencoder. I want you to implement a variational autoencoder on your own by running the code and trial change a couple of things and apply a variational autoencoder to dimensionality reduction and visualization as well. If you're joining us late, again, I just want to point out that the code that I'm talking about is in this website, revo.ai/tapia20, and you will have access here to the code and the slides and other number of things there. Okay, so a variational autoencoder is used sometimes as a generative model. What we mean by that is a model that can generate data, say X, that follows a particular distribution based on an input or a stimulus. And we call that distribution or stimulus input Z. And so this is following the concepts proposed by Kingma Welling in 2013, which show that we could perhaps learn to approximate something like a posterior distribution, for example. In this case, coming from Bayes' theorem, we have the prior distribution, Z, a distribution of the input stimuli. We're going to call Z also the latent space, if you will. So Z is this space that where the representations exist. And so we can ask ourselves, what is the probability of X given that we observe this latent representation or this Z data? And can we, if we have a sample data point X, can we retrieve, or what's the probability that that comes from this particular latent representation? And so we can model these problems and approximate them using a number of tricks. One of them, it's called the parameterization trick. And so we're going to use Q, that is an approximation to this posterior, while the probability of the latent space Z is actually also approximated as isotropic noise with zero mean and standard deviation sigma squared multiplied by the identity matrix. So this is like a diagonal matrix. It only has sigmas in the main diagonal. Okay, so with this in mind, we can make an approximation to this latent space Z and its parameters. The loss of the variational autoencoders in terms of the KL divergence, again, we don't have a lot of time to talk about this, but I encourage you to read about the KL divergence. And we can also include in the loss the expected value of the loss in the decoder, where we're trying to make this expectation as small as possible while maximizing the KL divergence. So, because these are not quite directly, or there's not a closed form for these formulas, for these equations, there are ways to approximate the laws like this. By plugging in or using the reparameterization trick, we can simply arrive to these nice and easy laws that is an approximation, of course, to the actual laws. So we split the loss of the decoder and the loss of the encoder in these two. So this comes from the KL divergence approximation using the reparameterization trick, and so does the one in the decoder. Okay. So what we're really learning in their using their parameterization trick is we're trying to learn the parameters of the latent space. So we said that z is this variable that comes from a latent space. But that latent space has a distribution, and the distribution of that latent space is given by mu and sigma. If we can only learn the parameters of that distribution, we could actually produce or generate data that follows that distribution. So if we have, for example, the number 4 as input, we can train an encoder to learn the parameters in this latent space that could produce a number 4. And that's kind of cool. So let's do this with a simple or smaller, rather not too deep variational autoencoder. Just a finite neurons, and then 2 and 2, only because I want to visualize this in 2 dimensions. So we're encoding down to finding a latent representation in 2 dimensions. So that means that Z is in a 2-dimensional space, and its distribution has its mu and sigma have 2 parameters or two elements. So we represent those, and we have a sampling that pulls data from those parameters, using those parameters, and produces something. And if that something cannot be reconstructed back to 4, then we can retrain until we can always find the correct parameters of this latent space that can produce the number 4. So for this, we need to define the sampling layer, this green one, that is going to be the z-mean, z-log var that comes from these parameters. And the mean and the log var come also from these items, the log variance and the mean. So we're trying to learn those. We can define a batch of data and retrieve the dimensions given the z-mean. So we know if the mean is 2 dimensions, we know that that is the latent dimension. And we can also get epsilon, which is this part of the reparameterization trick right here. That is something that is multiplied, or something that's multiplied, so we draw from there. So it returns the z-mean, e to the 0.5 log var times epsilon, which is a way of using these parameters to pull from a distribution that follows these parameters. Moving on. After we define the sampling layer, we simply follow the same steps as before. We define original dimensions, the latent dimension 2, set a number of epochs to train with, batch size 128. You can change these parameters, of course, as you wish. And one thing that is different is that the input data is going directly into this dense layer, as we specified right here. It's going to the dense layer followed by a ReLU activation here. But then that goes, that data goes into another dense layer, 2 dense layers. One is supposed to learn the mean, and the other one the log variance. So those are the parameters of the distribution of the latent space. Okay, and so Z, which is the lambda, which is the latent space variable that we pull from, it's going to call the sampling because it needs these parameters to sample from that distribution with those parameters. And so the encoder is supposed to take an input and produce the mean, or the approximated mean, the approximated log variance, and a sample from that distribution. And from there, we're gonna take now and produce the decoder, which also takes the latent dimension, or the latent space of 2 dimensions. We want to display this, and construct a dense layer followed by another one that goes from the intermediate dimension to the original dimension in a sigmoid activation. So we reconstruct back to the 0 to 1 range. and that is going to be the decoder. So we can call the output of this something that uses the encoder with the input, but it only takes the last argument. This is the 0 argument, the 1 argument, and the third argument, 0, 1, 2. So it takes the data that was generated from this distribution with these parameters, and that is going to be what is going to be decoded. And so the model is supposed to take that as a reconstruction. I hope that makes sense, because it is kind of interesting that we're learning the parameters, we pull from those parameters, and that is a reconstruction in our variational autoencoder. One last item is defining the losses. We can actually pull this off. And we're going to define the reconstruction laws and the two parts of the encoder and decoder law. So I put the formula here back just for reference, in saying that this part of the encoder comes from the KL divergence, remember? And so it's a KL loss, and it's 1 plus the low Z log var, right? It's right this, and then the square of the mean minus the exponential of the Z log var, because this is logarithmic, it's canceled by the exponential. And then we add this together, and then we divide it by 2. Okay, the last part is simply the loss of the decoder, which is approximated perfectly, well, almost perfectly, with the mean squared error. Okay, and so the total loss is the reconstruction loss and the KL loss. And when we add these laws, we can compile and train with an optimizer like Atom, RMS prop, SGD, as we have talked about this before. When we fit with the X train as the data, and the validation that is the X test. I believe there might be a typo in my slides here, so I want to make sure, because you have the code, I believe this should have another X train right here. Okay, so we have epochs, we have batch sizes already defined earlier, and we're ready to train. This right here, when you stare at this picture, this is what we can observe if we use the parameters of the latent space and simply go in a line, traversing it, and reconstructing from there. So if I go from -4 to +4 in Z1, and I stay at 4 in Z2, this 0 changes to an 8, to a number 2, and to a 1. And if I go downward, that 1 becomes a 7. If I go left, that 7 becomes a 4 or a 9, then a 4, then a 6, and then a 0. Another way to look at this is to look at the reconstructions. If you look at these reconstructions, you can see that most numbers are there. But something happened here to number 8. This is the input 2, and it produced an 8 shape. So this is completely off. This 4 was input, and it produced this thing that looks like a 9. This still looks a little bit like a 4, but these 9 and that don't look much alike. So what can we do to fix this? If we look at the 5-layer encoder and look at the 2-dimensional representations, this is how they look like. If you can see this, there's certain overlap, and that is producing this trouble. And if we look for number 8 and number 2, number 8 seems to be this pale yellow, number 2 seems to be a green. There seems to be a high overlap between the 2 and the 8 right here, and also number 2 is over here. So to fix this, let's make it deep. If we make a deep variational autoencoder with a ton of layers, like the one shown on the screen. I'm just going to trust that you have the code from the resources, and then we can just skip through this and go straight to see what the latent space looks like. These looks more well-defined. There are nicer properties of the data, as you can see, and perhaps it's clear if we look at the reconstructions. Here you can see that the 7 is the 7, 2 is still 2, 1 is still 1, that's 0, 0. And these 4s still have a little bit that looks like a 9, but in this one I can claim that that is a 4 rather than a 9. And again, one of the things that you may be observing is that they are sort of losing some type of detail. Do you see that? This number 4 lost its tail, for example. And that is something that we need to be very careful about. And one of the reasons why people use variational autoencoders is to denoise data. As you can see, if this 4 is considering this tail as noise, it got rid of it. If you consider the 0, that little tail up there, as noise, it certainly moved that away. If you think that having a 9 sort of in a rotated angle, this 9 reconstruction sort of fixed that angle a little bit. Did you see that? And if we look at the latent space, it seems like to be almost a perfect shaped squared here, and things are more spread out. Definitely the 8s and the 2s that were tied together before still remain close, but they're not overlapping that much. So this is a much nicer representation of a latent space with a 21 layer autoencoder. And again, I'm just repeating this carefully. We're asking too much of these autoencoders. We're asking them to reduce huge matrices to 2 values alone, and expecting them to produce very nice structures when they know nothing about labels. So this is amazing. I hope you can see that. Reflecting upon what we just saw, and knowing that we could potentially generate data from a variational autoencoder or from a regular autoencoder just by simply traversing the space. We pick whatever parameters that we want and we decode them. We generate samples from the distribution, and we can generate as much data as we want, which is usually called data augmentation. What do you think the risks are when we generate that much data? I want you to think about it and perhaps come to a unanimous conclusion among ourselves that perhaps the dangers of having data augmentation is that if our distribution is biased, that the data that is going to produce, it's also going to reproduce that bias. And whether that is something that we intentionally wanted or not, that is something that we need to be careful about. Usually, biased data should be avoided at all costs. And I say usually because sometimes we need bias to fix something that is broken in the world. For example, think of something legal like affirmative action that is introducing bias in certain aspects so as to fix something that was broken before, if you know what I mean. So there are some times that we need to add bias to fix things, but oftentimes, and the majority of the times, bias is going to be a bad thing. So we need to be careful about our data, and even if it's not our data, we need to be observant of being good professionals in our field and have a little bit of common sense and make an effort to make certain types of validation. I'm going to stop here, and I'm going to say a little bit commercial on my side. I am looking for PhD students and postdocs that are willing to go and embrace complex, time-consuming research on deep learning. And I have some opportunities posted here on www.baylor.ai. But I'm open to other areas of research as long as they align with what I'm doing. So if you want to know more, please go ahead and check that out. I'm also going to make the commercial that most of the content in this tutorial came from my upcoming book. This book it's available for pre-order right now. It's a brand new book, and I managed to get a 20% discount for the beautiful people of Tapia in this conference. So if you want to pre-order the book, go to the same of the resources page. I will update it there and post a link to a textbook if you want to order it and have access to the code and make use of this 20% discount code. I will be willing also to provide a free copy to you if you are willing to provide a review for the book. So if you're interested in actually reviewing it and provide an honest review, you can also send me an email and we can get in touch and talk about it. Well, I'm gonna stay here for a few months to answer a few questions, but that is all for me. Thank you for being here on this day and attending this tutorial in the Tapia Conference 2020. Peace.